Hello. Am I audible?
Hello, sir.
Okay, so I can see that we do have among us Professor Shamim Kaisar, who is the chair of the session. Hello. Am I audible?
Yes, sir.
Hello, sir.
Okay, so I can see that we do have among us Professor Shamim Kaisar, who is the chair of the session. Hello.
Yes, Mufti, you are audible. I'm chairing the session. Thank you. So first of all, hello, Mufti, can you hear me?
Yes, I can hear you.
Okay. So
Please go ahead with the session. Yeah.
thank you. First of all, I would like to welcome all of you to this session. The title of the session is AI and Informatics in Healthcare. So there are 5 papers in this session. I would like to request all the author to present the paper within 10 minutes. So the first paper of this session is paper ID 91, a non-parametric model for forecasting life expectancy at birth using Gaussian process. I would like to request one of the author to present the paper.
Everybody has the permission to share the screen, so please try sharing the screen. If you have any difficulty, just write in the chat. Yeah.
I'm Famidi Samairi, and I'll be sharing the screen.
Yes, your screen is visible.
May I start?
Yes, please start. Your screen is visible.
Good afternoon, everyone. I, Famidi Samairi, would like to take the opportunity to start the presentation on behalf of my co-authors. Our topic is a non-parametric model for forecasting life expectancy at birth using Gaussian process. Life expectancy at birth is the average number of years that a newborn is expected to live if current mortality rates continue to apply. Life expectancy needs to be forecasted to plan for pensions, health, and social services, as well as resource planning for long term. Life expectancy not only reflects the medical advancement, which leads to higher lifespan over the year, also the various factors such as economic, education, geographical, and environmental condition. We have treated life expectancy as a time series and used GPR to forecast future values of the different countries' life expectancy.
Apologies. Can you reshare the screen, Famida, please?
Yes. So the question arises, can a non-parametric approach be introduced to predict life expectancy at birth? And is it possible to find similarities between countries in the same income level and dissimilarities between countries in different income levels? Our study will contribute to predict life expectancy up to year 2040 and finding similarities in life expectancy between same income groups. Analysis of life expectancy trend to identify progress for different countries. Now, what is Gaussian process? Gaussian process is a set of random variables with a joint Gaussian distribution while there are finite number of elements. Here, the multivariate Gaussian distribution is determined by mean function and covariance function. Gaussian process can be used for regression problems. Gaussian process regression models are non-parametric kernel-based probabilistic models where, rather than calculating the probability of distribution of parameters of specific function, GPR calculates the probability distribution over all admissible functions that fit the data. The figure here shows functional distribution of covariance function based on how many observation points are fed into the process. More data points shaping the distribution for better fitting and the standard deviation region getting narrowed. To set up our distribution, we need to define mean and covariance matrix. In Gaussian process, it is often assumed that mean equals to 0. To estimate the covariance matrix, we require covariance function k, which will describe the shape of our distribution and determine the characteristics of the function we want to predict. We require multiple kernels to handle multiple features of our life expectancy data. To define long-term smooth rising trend in the distribution, we used radial basis function. A rational quadratic kernel is used for medium-term irregularities, and to define the noise in the data, we used a noise model using the white kernel. The functional distribution of the prior and posterior distribution of our combined kernel is shown here in the figure using Bangladesh life expectancy data. We can observe an excellent fitting of our data. We used the cross-validation method to evaluate how our model is performing on predicting the life expectancy for a given country's data. To cross-validate our prediction model, we split our dataset into two parts. As we have 60 years of life expectancy data from each country, we used the first 40 years of data from 1960 to 1999 to fit in our prediction model and predicted the life expectancy of the next 20 years from 2000 to 2019. We call this in-sample life expectancy. Then we cross-referenced with the actual value to evaluate our model's performance. For instance, in-sample life expectancy for Bangladesh is shown in the figure here. The data source that has been used in this research is collected from World Development Indicator, which are a set of development indicators compiled by the World Bank from officially recognized international sources. The dataset contains data of 165 countries starting from year 1960 to 2019. And for income level, we have chosen 27 countries and divided them among 4 gross national income per capita level. Here, 4 income levels are low income, lower middle income, upper middle income, and high income. Countries with a 2020 GNI per capita of $1,045 or less are classified as low income countries. $1,046 to $4,095 are classified as lower middle income countries. $4,096 to $12,695 are classified as upper middle income countries. And finally, countries with a 2020 GNI per capita of $12,966 or more are classified as high income economies. To verify our prediction performance, we have shown the in-sample life expectancy of lower middle income and high income countries. For lower middle income countries, we can see excellent fitting of our model. Same thing can be visible for high income countries in sample life expectancy. The predicted value and the original value are really close. These are the combined life expectancy of 4 different income levels. The top left figure shows the combination of predicted life expectancy for the selected low-income countries along with the aggregated low-income countries' life expectancy. Here it can be seen that almost all the countries trending towards 60 to 70 years, ranging 2040. Among the selected countries, the trend of Yemen Republic was slightly different. It's worth mentioning that its GNI per capita was the lowest of all the countries. The top right figure depicts a combination of forecast life expectancy for selected lower middle income countries, as well as aggregated life expectancy for lower middle income countries. Just like the trend of low income countries, lower middle income countries also have a similar trend towards age 73 to 80 at 2040, except for Zimbabwe. It can be explained by the fact that Zimbabwe's GNI per capita is close to the merging of low-income and lower-middle-income countries. As a result, there was a considerable difference in life expectancy between other countries and Zimbabwe. The bottom left figure shows the projected life expectancy for selected upper-middle-income countries with aggregated life expectancy for upper-middle-income countries. Except for South Africa, all the selected countries showed a similar uprising trend towards age 73 to 80 in the prediction. As it is known to all, as for South Africa, long history of adversity could be a factor for having diverse life expectancy, which affected our model. The forecasted life expectancy for selected high-income nations is shown collectively in bottom left figure along with the aggregated life expectancy for high-income countries. Every country showed similar life expectancy at 2040, ranging in between 78 to 89 over these years, with little deviation except for Saudi Arabia. As for Saudi Arabia, during the 1970s and 1980s, the economy grew rapidly, fueled by huge earnings from oil exports. This is reflected in the rapid growth in the life expectancy, thus affecting our model. So in the conclusion, I would like to say Gaussian process regression is a really powerful non-parametric Bayesian approach to regression, and we use this to predict the life expectancy of multiple countries up to 2040. Even though it has a cubic complexity, GPR has the power to work exceptionally well with few data points compared to other regression models. We combined RBF and rational quadratic kernel as our selected covariance function and created a complex kernel and chose appropriate hyperparameters for the best fitting of our data. We verified our model by cross-validation using 40 years of data for test data and 20 years for validation. The prediction line on the validation dataset showed close correlation to the original line, indicating excellent fitting of our model. The rise of the life expectancy varies for different income group, but showed similarities for same income group. These are the references that we used in this presentation. I would like to end my presentation here. Thank you everyone for your valuable time and kind attention. If you have any question, please ask. My co-author Prantu Biswas will carry on with the question answer from here. Thank you.
Dear audience, if you have any question, please feel free to ask.
Can I just have a quick curiosity, yeah?
Sure, sir.
That is, well, you have applied Gaussian process here, but do you actually see that if there are any other processes that can be used in remodeling the prediction of the life expectancy?
Can you please repeat the question? I couldn't clearly hear it.
In your opinion, are there any other modeling techniques which would allow you to predict it with similar accuracies?
I think there are many other approaches already have been done to life expectancy prediction, but most of them are done using probabilistic model. Sorry, my bad, no, parametric model. So our approach was non-parametric model to see the high level of accuracy which couldn't so far achieved by any parametric model so far. And we didn't check other non-parametric approach so far for this prediction. Approach already have been done to life expectancy prediction, but most of them are done using probabilistic model. Sorry, my bad, no, parametric model. So our approach was non-parametric model to see the high level of accuracy which couldn't so far achieved by any parametric model so far. And we didn't check other non-parametric approach so far for this prediction. Approach already have been done to life expectancy prediction, but most of them are done using probabilistic model. Sorry, my bad, no, parametric model. So our approach was non-parametric model to see the high level of accuracy which couldn't so far achieved by any parametric model so far. And we didn't check other non-parametric approach so far for this prediction. Approach already have been done to life. Most of them are done.
I think the answer is in a loop now. It's repeating again and again. Mufti sir.
Yes, Mufti. Can you check with this one?
Yeah, that's fine. That's fine. Yeah, I think that, well, the YouTube links are open in people's this thing, and that is something which might be.
The answer is in a loop now. It's repeating again and again. Mufti sir.
Yes, Mufti. Can you check with this one?
Yeah, that's fine. That's fine. Yeah. I think that one, the YouTube links are open in people's this thing, and that is something which might be.
The answer is in a loop now. It's repeating again and again. Mufti sir.
Okay, I think the problem resolved. Anyway, so let's move to the next presenter. This is the paper ID 96105, a pyramidal approach for emotion recognition from EEG signal. I would like to request one of the author to present the paper. Okay, I think the problem resolved. Anyway, so let's move to the next presenter. This is the paper ID 96105, a pyramidal approach for emotion recognition from EEG signal. I would like to request one of the author to present the paper.
Actually, well, if you have the YouTube running at the background, please.
Okay, I think the problem resolved.
Close the YouTube.
Anyway, so let's move to the next presenter. This is the paper ID 96105, a pyramidal approach for emotion recognition from EEG signal. I would like to request one of the author to present the paper.
Actually, well, if you have the YouTube running at the background, please close the YouTube.
Hello, Mufti sir. Is my voice audible?
Yes, it is now. Perfect.
Is my screen sharing is visible?
Yes, it is.
Okay, shall I start it, sir?
Yes, please go ahead.
Okay, good evening, one and all. Welcome to everyone. My name is Tejaswini MS, Research Scholar, University of Mysore, working under the supervision of G. Hemanta Kumar, sir, Vice Chancellor
Hello,
of
Mufti
University
sir.
of Mysore.
Voice audible?
Sir, but again it is
Yes, it is
repeating.
now. Perfect.
Is my screen sharing is visible?
Yes, it is.
Okay, shall I start it, sir?
Yes, please go ahead.
Okay, good evening, one and all. Welcome to everyone. My name is Tejaswini MS, Research Scholar, University of Mysore, working under the supervision of G. Hemanta Kumar, sir, Vice Chancellor
Hello,
of University of Mysore. Voice audible?
Sir, but again it is
Yes, it is
repeating.
now. Perfect.
Is my screen sharing is visible?
Yes, it is.
Okay, shall I start it, sir? Okay, good evening, one and all. Welcome to everyone. My
Mufti,
Yes.
I think disconnect the YouTube link if this is creating problem. Just record the session and later on just upload it in the YouTube.
But I think that, well, there are people who are also attending the YouTube session.
For
so-
YouTube sessions. Okay.
Yeah, but well, I
Got
think, Tejaswini, well, it is only at your end, there is some problem. So can you please check that if the YouTube link is open in multiple browser windows?
At my end,
No, it's
Sir,
actually.
is it
No,
okay
no.
now?
Yes, it's okay now. Yeah.
Okay. Sorry
Let's see
for
how
the
it proceeds.
inconvenience.
Yeah. Okay.
Sorry
So
for the inconvenience. Let me start it from first.
20 slides, but I'm afraid that you will have to do it in 8 minutes. Okay. So please take care of the time.
Okay, sir. Sure. I'll do that. My research article is entitled "The Pyramidal Approach for Emotion Recognition from EEG Signals." And these are my outline of my presentations. And starting with the introduction, in the recent years, one of the leading technologies which is earning greater mode of interest in the various fields of effective computing is the brain-computer interfaces, including various applications in the real-world scenarios. And effective computing is one of the major branches in the field of artificial intelligence, where it measures about the details about arisings or the influences of emotions, and also it plays an essential role in decision making. And in the expanding literature of BCA sectors, it has recognized that analysis of emotion is an empathetic aspect in developing various applications of entertainment, marketing, medical diagnosis, education system, and smart environments. And coming up with what is emotions? Emotions are essentially important for human interaction. They are powerful sources in determining the shapes, outlooks of how we feel about particular events around us with the external environments. And identifying these emotional intuitions ranging from basic to advanced behind every several application is a symbolic and challenging responsibility of every researcher in the field of affect recognitions. And from this point of view, our research study focused on developing and exploring a machine learning model for recognizing emotion through mode of BCI technology known as electroencephalogram signals, that we call it as EEG signals. And it could be the best choice for the emotion recognition by virtue of its inherent characteristics, as difficulty in counterfeiting, faking the emotions when compared to other mode of emotion recognitions. And coming up with the general architecture of emotion recognition based on EEG signals, it has the following steps. First, the basic step is inducing emotions, recording EEG signals, and pre-processing of EEG signals, where other artifacts are removed in the pre-processing, like head movements, eye blinks, hand movements. This all the unnecessary features are removed. Only the relevant features are captured in the pre-processing of EEG signals. And most important and essential part is feature extraction, that is EEG feature dimension reduction from feature selection or feature transformation techniques, it could be. And final most step is study of emotional patterns and classifications. And in the above all mentioned phases, each one of them is a bottom line factors in analyzing an emotional states. But importance of emotions, motivation behind this work is recognizing emotion from psychological signals is a significant task when compared to other mode of emotion recognition, because facial expressions or speech can be counterfeited or faked or forced, or it can be annotated at some times from the individual. So the psychological signals could be very true emotions and very true data which can be analyzed for further. And developing demand for new feature representation techniques could be a limited source in so far studies. And suitable and feasible algorithms also should be developed to meet the challenges in building an efficient EEG based emotion recognition system. And challenges could be in the area of machine learning. Main thing comes with the dimensionality curves. So higher dimension data may cause many different problems, many different issues. So dimensionality reduction could be a very great challenge in building or developing any emotion recognition system on various applications. So extracting essential features with dimensionality reduction without loss of data is a challenging task. This is what we followed in our proposed architecture. And these are some of the application, and these are some of the greater work by the greater author with the different types of feature extraction and classification, and with the different types of dimensionality reduction approaches. And this is our architecture of proposed methodology. As our title is entitled pyramidal, so our signals also reduced in the pyramidal way in the different levels. We have taken directly the preprocessed EEG signals.
Sorry to disturb you. Sorry to interrupt here.
Yes, sir.
Your slide is just focusing on the first slide, actually. The title.
1 second, sir. Right now, sir? Is it in 10th slide, sir?
It is in the slide number 1. I don't know about others. Can others confirm, please?
Yeah, it is in slide number 1. And now it is in 10.
Shall I continue, sir?
Yes, please. Yeah.
Okay, this is our architecture of proposed methodology. As our title is pyramidal approach, we have given a unique name for our proposed model. That is, our data is reducing in the pyramidal way. It is reducing the different 5 levels of iterations, and we have taken the pre-processed EEG signals from the benchmarking data set, and we have given, after the 5 levels of reducing iterations, we have given those input features to GRNN, generalized regression neural network, to classify these 4 different emotional classes: calm, boring, horror, and funny. And next is to do this, we have inspired by one of the numerical analysis approach of mathematics, that is interpolation. It is nothing but a differencing approach. So the study of relevant features from high dimensional time domain EEG signals, and the study is considered in differencing discrete samples of given database discontinuously. I mean, the samples vary from one another. The samples of input signals, the samples of input data is varying from one another. So we have to do the discontinuous differencing approach in the closed loop of intervals. I mean, we are doing only the 2 successive values to be differenced. That is a consecutive samples of even and odd terms in the different levels of iterations, for reducing the high dimensional data into half of its samples successively in each level of iterations. And since our input data itself are discrete in nature, the results also obtained are discrete in nature. And this was inspired from one of the method called Newton interpolation forward differencing. And this is the flow diagram of how 5 different levels of forward interpolation for reducing dimension is used. This is sample number. I mean, 38,000 is the data collected while the people are playing a computer video game for 5 minutes. And see, in the first level, we have taken closed interval of 2 samples, and successfully we are differencing that to 19,000. And in this third step, it's go for 8,000, and fourth 4,000, and finally we come for 1,000 features. And this is the general notation of proposed interpolation, that is delta n minus delta n plus 1. I mean, where n is the number of samples from each subject from 4 different classes. Delta of x could be the different level of forward difference operations, and delta n and delta n plus 1 could be the values in each samples. I mean that odd and combination of odd and even terms. And these are the 5 different levels of forward difference interpolation iterations for dimension reduction we followed: delta 1 to delta 5. And we named it as first level of forward difference, second level of forward difference, third level of forward difference, and fifth level of forward difference. And we have taken the pre-processed EEG signals, EEG features in the time domain of all subjects in each class of emotion, which has reduced from 38,000 to 1,187 features. And finally, we are given that input features for GRNN for classifying, which is good at GRNN is preferred because of its high performance, and which is good at prediction task, and it also manages non-stationary and non-linear data, because EEG signals are non-stationary in nature. And experiment and analysis we followed with the MATLAB. We followed the standard training testing division of 80-20 ratio. And comparative results could be, so the great authors have worked on different dimensionality reduction methods along with different classifiers with different benchmarking data sets. Sorry, I have missed the data set slide. The data set is the type of signal recorded is EEG, and number of channels was 14. The sampling rate was downsampled at 128 hertz, and number of subjects was 28. With and the people was playing 5 minutes of computer game, which was from the computer game was relatable to 4 different emotions: funny, horror, calm, and calm. We have 38,252 samples for each subject in every classes. While following the interpolation, we have cut down the last 252 rows of data, and we have taken 38,000 of data. And comparative, when coming to comparative analysis, we have compared channel wise comparison also with other people. That is people with all different channels with different classifiers. They have good accuracy, but when our method was performed very good when compared to other methods. Since it was a new method, we followed inspiring from numerical analysis of mathematical approach, and our intuitions was analytical research of mathematics is relatable to our proposed work. And conclusion could be the main purpose of this study was to reduce the higher dimension data into smaller.
Maybe there are some technical issues at her end.
Yeah, I think so.
Yeah, because I do not see her. So maybe there are some technical issues. Please move to the next one.
Okay. Let's move to the next paper, paper ID 54, a hybrid transfer learning and segmentation approach for the detection of acute lymphoma. I would like to request one of the author of paper ID 54 to present your work. Paper ID 54. Is anyone from paper ID 54? So let's move to the, I think, paper ID 54. I mean, the authors are not present over here. So let's move to paper ID 83. Mufti, am I audible?
Yes, Shamim sir, you are audible.
Okay.
Yes, you are. Yeah.
Okay. So, I mean, the paper ID 54, anyone? Any authors are present over here?
No, it doesn't look like.
Okay. So let's move to the paper ID 83, icon date 2, and improve conjunctivitis detection portable healthcare app powered by artificial intelligence. I would like to request one of the author to present this paper.
Yes, I'm present. Am I allowed to share the screen?
Yeah.
So it is
I
showing you
think-
cannot start screen share while other participant. Yeah.
Okay. You can share.
So is it visible?
Yes, your slide is visible.
Okay. Good evening to all the eminent dignitaries and the participants present in this conference. My name is AII2022 Chatterjee, and I am going to present you our research work on the title AII2022, an improved conjunctivitis detection portable healthcare application powered by artificial intelligence. So let us quickly go through the contents of our presentation. First, we will discuss about a little bit of the introduction, then our main contribution purpose of this research, the methodological pipeline we have used while while making this application, the results that we have achieved after the research that we have done, the conclusion, and the future work, if any. So first of all, we all know that conjunctivitis is a very common ocular disease that is found in the sclera region of human eye. And it is very important to treat the disease in an early stage, especially in this recent phase of COVID-19, where recent researchers have found that COVID-19 positive patients are also getting symptoms of conjunctivitis. So it's better to actually treat it on the earlier stage. So in this presentation, we are going to present our AII2022 version 2, which is an advanced and improvised solution of the application that was previously made back in 2021, which was AII2022. Now, what is the main contribution and purpose of this research? Firstly, our major contribution was creating a labeled data set in the internet, because in the internet there is no such images that has been found for labeling the healthy as well as infected eye. There is a scarcity of images and open images data sets. So our primary aim was to make a much more data set with dynamic images, so that it becomes easier for the research purposes. Secondly, a comparative study has been done amongst all the deep learning models, and the best model has been chosen for the application that has been made. And finally, of course, the release of the mobile application, as we said, which is AII2022 V2 and is available in Android devices. Now, let us quickly go through the methodological pipeline of our research. Firstly, as you can see, the user can click the images or take from the internal storage of their mobiles, and then the images which are taken are then fed into the system, and it's been pre-processed. Now, image pre-processing is much more needed in any image classification, because the images that are took are mostly using a very orthodox and very non-uniform image taking techniques. For example, the images that we took are non-uniform and are taken using hands, so it's not proper. Another reason is that the images that are taken could have a much amount of noise. So removing the noise and getting the perfect shape and size of the images is very important before any classification. So here we have first taken the images, and then the images has been cropped, taken only the sclera region part of the eye, because there only we can detect the conjunctivitis, and we have used an open source cropper known as freehand cropper, and then the images were pre-processed. The pre-processed images, as you can see, is then saved inside the local storage. From that local storage, the model takes the images and classifies. And here we have used ResNet as the deep learning architecture, because we have achieved a much higher accuracy other than rest of the models. So we have chosen ResNet as the deep learning model, and then the model obviously classifies successfully whether it is conjunctivital positive or conjunctivital negative. As I said earlier, that the deep learning model we have used is ResNet, and we have used all the three major architectures of ResNet, which is 18, 34, and 50, and of course, which are named after the number of layers, the depth of the model. The reason for taking a ResNet is, of course, primarily is that we have achieved a much greater accuracy for the classification other than the models that we have used, and also it solves the degradation problem, which means that the deeper the neural network, the higher the training error goes. So that is another one of the reasons we have taken ResNet. And here you can see a modified ResNet 18 architecture. So as we're talking about a very increased and much dynamic data set, here we can see a glimpse of the data set that we have used, the pictures, and we have taken almost more than 310 data sets, raw data sets taken from very eminent eye hospitals and clinics in our city. And these images were all the images taken from the patients that were there. And these images were taken also, as you can see, these images are totally non-uniform with no proper shape and size. So it was cropped, then it was pre-processed, then only you can use. So it gives a dynamic approach to the research where you can, there's no such proper binding from the internet, and of course increase the number of data sets in the field of the research. So now we come to the results of this experimentation, where we have trained our models for 50 epochs with 10 folds cross-validation learning, and we have achieved loss and accuracy score from the process. And we trained our ResNet model, as we have said earlier, on the conjunctivitis dataset. We have trained of the depth of 18, 34, and 50 respectively, with different learning rates. So now you can see all the our model architectures with different run rates, giving the training, validation, and testing accuracy, F1 score, and ROC values with respect to all the architectures, and again with respect to the learning rates. Here is, as you can see, the graph that has been obtained, the mean training accuracy, the training loss, mean training loss, the mean validation accuracy, and mean validation loss of the ResNet 34 model. And the shadow region that you can see is nothing but the standard deviations of the values during the 10-fold cross validation system. And of course, this is the same as that of the ResNet 18 model. Now, finally, coming to the conclusion of our research, as we have seen that we have successfully classified the conjunctivitis problem, whether it's conjunctivitis or not, and 3 experimental models, as we have seen, 18, 34, and 50. But in our application, we have used ResNet 18 model trained as a learning rate of 1e to the power -4 in our application, because we have to keep in mind about the storage management of the model inside the application. So for that, we have experimented. I've seen ResNet 18 works perfectly in this learning. And of course, our model has attained the best accuracy of approximately 95% in validation and predicts almost 97% images correctly in the testing. Now, coming to the future work, we can devise an automated image segmentation algorithm to segment the images without using the freehand cropper that we have used, so that it directly, you just don't have to do anything, don't have to crop, just click the images, only the scale up at the eyelashes, eyebrows are automatically omitted. And of course, you can further study by getting the intensity of the images and classify it, whether the conjunctivitis is in a moderate stage, in a mild stage, or in an advanced stage. And finally, of course, we can explore the performance of range of different deep learning models in the future, so that we can achieve a much greater accuracy in this field of research. So thank you. And any questions?
Thank you very much. Dear
Thank you,
audience,
sir.
if you have any question, please feel free to ask. So I have just a little question, I think. I mean, in your data set, is there, I mean, the people from different ethnicity or different region is included or not? Let's say the black people as well as brown skin, as well as, I mean, the white skin. Because, I mean, for black people, most of the cases, the eye color is different. I mean, the white. So have you included all these things?
No, because in our data set, we have to collect all the data sets in our own city. So practically, for detecting conjunctivitis, you just have to focus on the sclera regions and it will turn pink. So with respect to if other infections can be seen in any images, so it can be easily image segmented, and only the pink portion can be found and intensity can be achieved. So for different race and color, yes, of course, the data set, as you can, I can, if it's possible, I can show you that these images, as you can see, a little bit part of the skin is shown, which is black. With darker skin color, I can see in a proper way, not black, darker skin color, and some of them having a white skin. So primarily, I guess, like we haven't found any such differences in the with respect to skin colors. We have tried to maintain the uniform data set by focusing just around the sclera regions, not the other parts.
Have you implemented your model in mobile platform?
Yes, we have made the application. We have accepted. We have given that model inside the application, so that it becomes like the total application.
So how you have done the RAM management?
Sorry, what management?
I mean the management of the memory.
Management of the AII, we
Labour-
have created, like we have primarily, first we did was we taken the data set, we have stored in the cloud. You can either store in the cloud or in the
Okay,
internal
okay,
system
got it.
from the internal
Got it,
storage.
got it.
Cloud or
Okay.
internal storage, the model accepts it. So yeah, you just have to select the option.
Okay, thank you so much.
Okay.
So I would like to, the request, is anyone from the paper ID 54? A hybrid transfer learning and segmentation approach for the detection of acute lymphoma.
I'm sorry to interrupt. Am I supposed to stop the screen share?
Yes, please. Yes,
Okay.
please.
Thank you, sir.
So let's move to the ID86 ensemble classification for a four-way classification. Sorry, ensemble classifier for a four-way classification of Alzheimer's disease. I would like to request one of the author to present the paper. Paper ID 86.
Myself, Naushad here. I'll share my screen to present this paper. I hope it's visible. Okay, myself Naushad from University of Technology and Applied Science, Sultanate of Oman. I'm presenting this paper on behalf of my co-authors. Title of this paper is Ensemble of Machine Learning Classifiers for a four-way classification of Alzheimer's disease. Okay, just a brief about this disease. Alzheimer's disease is an incurable, life-altering and progressive neurodegenerative disease. It can lead to a significant decline in cognitive abilities, which in turn can severely impair an individual's personal and social life. According to latest World Alzheimer's report, around 55 million people worldwide are diagnosed with this deadly disease. This is not considering innumerable other cases which goes unnoticed or unreported. So this is, according to the report, is the 7th major reason for the cause of death globally. So discomforts includes memory discomposure, behavioral disorderliness, and various other physical issues causing vision and mobility complications. Not to mention the difficulties faced by the family members, which is very, very grave, taking care of the patient. So it is imperative to detect this disease at an early stage so that the suffering of the patient and caregiving family can be curtailed to a greater extent. So on this aim, what we have done in this work is we have proposed machine learning, traditional machine learning approaches to detect to classify this disease with the aim to see how far this can outperform the, recent days we have a propensity of applying deep learning algorithms for almost every problems, and they have performed well too. So we just wanted to see the application of classical machine learning algorithms and see how well it performs, because in our experimentations, we could see the simple ML algorithms, machine learning algorithms could outperform deep learning algorithms. So we have tested the efficiency of these ML algorithms both independently as well as two different ways of ensemble classification. So the ensemble classifier model that we have used is the max voting and probability based fusion approach. So what we have done is we have first considered an image of size 176 by 176 by 3 in 3 dimension that will go through VGG16 model without the top layer. So this will result in a feature dimension of this size 5 by 5 by 512, which will be considered in a subsequent machine learning classification process. We will not input a raw image to the machine learning classifier. Rather, we take the image and convert it into a feature through the application of VGG16 architecture. So we are just using this deep neural network for the purpose of feature extraction, not for the classification. So the process can be illustrated using this simple diagram. So where we have this MRI images as the biomarker for this disease, which will go through the VGG16 feature extraction module. And then we have several independent machine learning models. So here I'll briefly explain what is these two ensemble classifiers. One is the hard or max voting approach. The other one is the probability-based diffusion approach, which is also called as soft ensemble approach. So in the hard voting approach, all these classifiers will vote for any of the 4 classes that is there in this disease. And the maximum, so this is actually a max voting approach, as the name itself says. We will see the maximum vote by all the approaches, and accordingly one class will be selected. Whereas in probability based diffusion approach, we will see the probabilities of every class by individual methods, and based on the sum of the probability of every class, whichever is maximum, that will be considered as the ultimate class for the input sample. So this is what exactly we have done. And for the experimentation, we have considered the OASIS dataset, which has 4 classes, which is having samples based on clinical dementia rating score. The CDR score of 0 indicates cognitively normal, 0.5 indicates very mild dementia, 1.0 indicates mild dementia, 2.0 indicates moderate Alzheimer's disease. So the number of samples are as indicated here in each of these classes. So there are basically 4 classes for classification. The metrics we have used here is accuracy, sensitivity, and specificity. These metrics are highly useful, especially in healthcare analytics. Sensitivity or recall counts how often a test rightly predicts a positive result for people who have the condition that's being tested for. This is also known as the true positive rate. This measure also helps to discover the false negative rate, because 1 minus sensitivity is actually false negative rate. Also, specificity counts a test's ability to rightly generate a negative result for people who don't have the condition that's being tested for, which is a true negative rate. This measure also helps to discover the false positive rate. So having sensitivity and specificity computation results in getting 4 different very useful parameters needed in healthcare analytics. So we have used these metrics. So these are the results that we have obtained on independent run of these machine learning algorithms according to those metrics which I just explained. You can see here the simplest KNN algorithm got an accuracy of 91.2, random forest SVM XGBoost. So in fact, in paper, we have a detailed analysis based on this accuracy, why they are performing like this. So interested can go through that. The last result here is about the, ensemble classifiers. You can see here the last 2 confusion matrices here are corresponding to the max vote and probability based diffusion approach. You can see here the ensemble based classifier approached increase in the accuracy compared to the independent classifier, obviously. But what we have observed is the simple machine learning algorithm sometimes easily outperform the computationally intensive deep learning model. So it is not always one has to resort to deep learning models for simple classification tasks, especially when there is data scarce situations such as this healthcare analytics. We don't have enough samples in all domains. So conclusion is the best accuracy is of 94.92. 92 was obtained for ensemble classifier model consisting of these machine learning models. However, the best ensemble classifier depends on what data set we have, the hyperparameters of these models. So all this needs to be investigated. So these are our future scope for future avenues. Also, XGBoost algorithm was consuming a lot of time in our experimentation. So it would be interesting to see how this will perform if we apply any preprocessing such as the transformation to subspace methods or DCT, and then checking its performance for time and accuracy. A natural extension would be to observe these methods using various other ensemble techniques such as weighted average ensembling, stack generalization, etc. And we would like to see the performance going forward with the ADNI data set by considering MRI images from different planes. So that will give further insight into this problem. Thank you so much. If you have any questions, please.
Thank you so much for your nice presentation. Dear audience, if you have any question, floor is open.
I have a simple question. Can I ask?
Yeah,
Yes, please.
Okay, thank you very much for your nice presentation. It was really nice. I'm just wondering, KNN gave you the, in many cases, KNN gave you the best result. I'm just wondering how you select the value of K.
Value of K, we actually, tried by varying the value of K. 2, 3, 4, like that, we have varied the values of K and then pick the one which gave the optimal result. That is why I mentioned all these algorithms. What we have presented is mostly for, default values. Some algorithms like SVM needs a lot of hyperparameter, tuning. So which was beyond the scope of this work. However, we are considering this as a future avenue and we will report it in some work very soon.
Okay, yeah. With these in line, I would like to ask you one more question. There's something similar that due to different parameter settings, you can have different result with random forest as well. In some cases, you found the best result came in random forest. So again, how many, how you actually found the best result there? How many parameters selection you tried or how you picked it?
With the random forest and SVMs, we just went with the default values for most of the hyperparameters.
Okay, then I would like to add that if you just try with some different settings, perhaps there might have a better chance, because I tried with some experiment with just few tweaking of parameters, the performance improves significantly. And in line, sometimes that's why it is better to try some non-parametric approach as well to get rid of these of parameter tuning thing. Anyway, thank you very much for your answer.
Yeah, thank you so much for your comment.
So any other question from the audience? Okay. So actually, my question is already grabbed by Arif. Thank you, Arif, for your question.
My pleasure.
Anyway, so we have 5 papers in this session. Unfortunately, we have not found anyone of paper ID 54. So, we have seen the paper presentation of, the forecasting life expectancy using the Gaussian process. And we have also seen emotion recognition from EEG signal and conjunctivitis detection using AI. That has been implemented in portable devices. And also we have seen, the Alzheimer's disease classification using ensemble method. So we are really sorry for interruption due to the technical problem. And I would like to thank all of you, especially each of you, for joining the session and make the session interactive. I believe we have learned a lot from the discussion. So thank you so much for joining the session. Now I'm moving to Mufti. Mufti?
Yeah, thank you very much, Professor Kaisar. Well, I completely echo your sentiment. I would like to thank everyone for your contribution to the session and overall to the AII conference. And given that today's session only we had one hybrid session, and referring to the program, tomorrow actually we have another hybrid session, which is going to take place 11:20 till 12:35 Italian time. And we have the session chair for tomorrow's session here, Professor Arif Rahman, and I would like to invite you all to that particular session. And in addition, there is a panel discussion, which is again going to go hybrid. And the panel discussion is titled as Applied Intelligence Towards Inclusiveness and Personalization for Students with Learning Disabilities and Autism. And that panel discussion is going to take place from 9 a.m. until 9:45 a.m. Italian time. So I would like to invite you all to also join that panel discussion online. So with this, I would like to thank Professor Shamim Kaisa for chairing the session, and I hope to see you all tomorrow during the hybrid session of the AII conference. Thank you very much.